First, to write the complete and net ionic equations for the following reaction between iron and copper bromide to create iron, bromide, and copper, we need to make sure the reaction is balanced, and it's not, because if you look at this, there are 2 bromines in the reactants but 3 bromines in the products. So to balance those, I'd need to look for a common multiple between 2 and 3 so that I could have the same number on either side. And I can get that by multiplying this reactant by 3 to get 6 bromines, and this reactant by 2 to get 6 bromines again. So now the bromines are in fact balanced. But the coppers are not. Look, 3 coppers on this side in the reactants, only 1 in the product, so I'm going to put a 3 in front of the copper. And then over here it looks like the iron's not yet balanced, because in the reactants there's only 1 iron, but in the products there are 2. So I'm going to add a 2 in front of the iron in the reactants. Now the reaction is balanced. There are 2 irons on both sides, there are 3 coppers on both sides, and there are 6 bromines on both sides. So at this point, this is a balanced, complete ionic equation. Well, I should say it's a balanced, complete equation. We're going to turn it into an ionic equation, and then we're going to write a net ionic equation based on that. Okay, so to write this as an ionic equation, we are going to have to write the ions that have been dissolved in solution as separate charged species. So let's look at those state symbols. The stuff in parentheses, this S, that state symbol means that this is solid iron. This S next to copper means that this is solid copper. But this AQ in parentheses following copper bromide and the AQ in parentheses following iron bromide means that there are ions that have been dissolved in solution. So if you were to be able to figure out what chemically this is in solution, this copper bromide, it would actually resemble, each copper bromide would resemble a Cu2 plus ion and a Br, actually 2 Br minus ions. So that's for each copper bromide. And you may be wondering where I got those charges from. This is a skill you should have at this point in the class. If you go and look at the periodic table, you'll find that bromine is a nonmetal. It's only 1 column away from the noble gases, so it's going to gain 1 valence electron when it forms an ion. So that makes the minus charge for bromine. And based on that, you can figure out that since there are 2 bromides listed in this ionic compound, this copper being a metal and this bromide being a non-metal, so that means that the copper is going to have a plus charge. It's going to lose electrons. How much of a plus charge is it going to have? Well, since there are 2 bromides and 1 copper, that means that the copper lost 2 electrons, so that it has a 2 plus charge, which exactly cancels out the 2 minus 1 charges of the bromides. So the overall charge of copper bromide is 0, and that comes from a plus 2 charge and 2 separate minus 1 charges. So that's how I know in my head at this point that I can actually break this up into 2 charges, and I know what the charges are. So these are the 2 ions that we're breaking it up into, and that's per every copper bromide that's in the reaction. So what's actually going to be required here is that since I have listed 3 copper bromides, I'm going to have to multiply the amounts of these by 3. So instead of having 1 copper ion, I'm going to end up having 3 copper ions. So it'll be 3 Cu2+. And instead of 2 bromides, I'm going to have 6 bromides. So here you see how you'd write out the complete ionic equation for the reactants. The solid reactants don't change. The ones that are solution do, and I'm just representing that in fact in solution copper bromide doesn't stay together. It gets dissolved, it gets ionized into two different ions. And bear in mind I haven't changed the number of bromides. There were 3 times 2, 6 bromides present, implied here in the reactants, and they're listed here explicitly in the ionic equation. We can repeat the same process. So if we have this species, or I guess it's not species, this compound, the iron bromide, which is dissolved in solution, if we break it up into its ions and list them as 2 separately solvated ions, we'd have 2 irons, and we'd have 2 times 3 is 6 bromides, again, listed. So we listed these 2 ions out separately. How do I know that this is iron 3 plus, instead of like iron 2 plus or some other charge? Well, as a neutral compound, there are 3 bromide ions. That means that the iron has to have a 3 plus charge to make this compound have an overall 0 charge. So that's how I know that it's iron 3 plus. Notice that the charge is balanced here, right? So in the reactants, I have 3 times 2, that's plus 6 positive charges, and 6 times negative 1, negative 6 charges. So 6 minus 6, 0 overall charge in the reactants. It's the same over in the products. It's an overall charge of 0. I have neither created nor destroyed charges going from products to reactants, and I can't do that. There's conservation of charge. So it makes sense that I've written it the way I have. So this is the complete ionic equation. Just abbreviating it for you. So that's the complete ionic equation. Notice, though, that there's some repetition here. So in the products, we have 6 bromide. In the reactants, we have 6 bromide as well. So these are, since they're present both in the products and reactants, these are called spectator ions. And it's kind of like they don't really do anything. They sort of hang out in solution while the other chemicals are actually reacting, and they're just like watching. They're spectating. They're not actually participating in the action. Notice that these other ions, or these other species, this iron, which used to be a solid and used to be neutral, is now a solvated ion. It's charged and it's in solution. Notice that this copper, which used to be a +2 ion and used to be in solution, AQ, is now a solid. And it's now neutrally charged. So if I wanted to write out what's changed and cut out the spectator ions, I would get the net ionic equation. So here is the net ionic equation written out, and the only thing I did is I removed the bromides. So what were the spectator ions? These bromides, I cut them out of the equation, and now I just have listed species that have changed. So like iron changes, the copper changes, but these bromides didn't, so they're not listed in the net ionic equation. So that's the whole process. It does rely on your ability to make sure that things are balanced in the chemical equation. It relies on your ability to determine what the ion charges are based on a compound's formula. And it also requires that you be able to identify what's changed and unchanged between reactants and products in a overall complete ionic equation. And that will allow you to identify things that haven't changed, these spectator ions, and things that have, everything else, and that everything else, the things that have changed, are what get listed in the net ionic equation. It's not as hard as you might think it is. It's just a lot of steps.